new video is about matrix exponentials. They're a new topic that we want to look at in order to construct more based on the fundamental matrix that we just did. So when we're solving linear ODEs in one dimensions, we have x prime equals ax, with a real number. Then we fix x at t0, in this case 0, and we say that it's x0, that is a real number. And the solution is x times exponential of at times x0. They're all real numbers, so we can freely do the multiplications in here. In higher dimensions, we have that x prime equals to capital AX, where A is a square matrix of size n. X at 0 is x0, where x0 is the vector of initial conditions. And we have that the solution is x equal the special fundamental matrix that we have just constructed times x0. We want to investigate if there is a relationship in here between the phi t and exponential of at. Exponential of at can be written as Taylor's series. It converges for every t infinitely long. That is 1 plus a times t plus a squared t squared divided 2 factorial plus a to the third t to the third divided 3 factorial, and so on. And this can be written as 1 plus sum from n equal to 1 to infinity of a to the n t to the n divided n factorial. Why don't we start directly the sum at n equal to 0? Because 0 factorial is a bit iffy. It's not really clear what it means. So we try to avoid that. But we can define for a square matrix the series that has the same shape. So instead of a being a real value, we now have a being a square matrix. Because a is squared, we can easily multiply a by itself. So now we have the identity matrix instead of 1, plus a matrix multiplied by t, plus a times a multiplied by t squared divided 2 factorial, plus a to the third t to the third divided 3 factorial, and so on. We can rewrite this, and we notice that I is an n by n matrix, a is an n by n matrix, so a times t is an n by n matrix, and every single term in here makes sense in the sense that it has all the same shapes of being n by n matrices, so we can sum them up. We do that, and we write it as I plus sum from n going from 1 to infinity of matrix A at power n times t at power n divided n factorial. Each single element of this matrix converges for all t for n tending to infinity. So it is a well-defined power series with radius of convergence infinity. So we're good in that sense. We define now the exponential of the matrix A times t as this series that we just introduced. So while for a scalar, a real value, the exponential of at has the property that it can be written as a power series, for a matrix, square matrix, exponential of at is defined as a power series. So there is a little bit of change between the exponential in the real values and the exponential in the matrices by how we define it. Let's check that it behaves as we expect it to behave. So the first step is we want to have it that the derivative with respect to t of exponential of at is equal to a times exponential of at. Does this work with the definition that we just introduced? Let's try. We compute the derivative with respect to time of the matrix exponential. This is the derivative with respect to time of the definition of the matrix exponential, that is the power series we just introduced. But we noted when we take derivatives in power series setting, if they are converging, then we can take the derivative of every element of the power series. So we get this. We get the sum from n going from 1 to infinity of a at power n, t at the power n minus 1 divided n factorial multiplied by n. So if we take A once out of this rule sum, and we simplify by the multiplication by n, we retrieve this, that is the sum A multiplied power series from n going from 1 to infinity of A at power n minus 1 times t at power n minus 1 divided n minus 1 factorial. It makes sense, but as usual, we don't want to write down the factorial of 0. So we take that element out of our series and we retrieve indeed that this is a times exponential of at. We also want to check that computed at t0, we have the equivalent of 1 in this context, that is the identity matrix. And this is trivially right because the infinite sum that we have is multiplied by t. So that is at t equal to 0, that is multiplied by 0, so it's 0. So the exponential of at computed at time equal to 0 is the identity matrix. This means that phi t that we have just introduced is equal to the matrix exponential of A, because they're both the unique solution of phi prime equal A phi and phi at 0 equal to the identity. Now I'm sweeping a little thing under the rug because we said that the solution is unique when we're talking about vectors. But we can think about matrices as multiple vectors one after the other. So this still makes sense. That means that if we have any linear ODE system, x prime equals a of x, x at 0 equals x0, it has a solution x0 equals matrix exponential of a times x0. I want you to check why we cannot write x0 times exponential of at. Does it matter? Does it not? It matters, and I'd like you to check out why. So now that we have the exponential, the matrix exponential, we would like to compute this thing. So as a first idea, we notice that the exponential of the identity, if we do it term by term, we notice that elements of the diagonal never go away from the diagonal when we multiply the identity by itself. Any multiplication of the identity is still the identity. So if we use a power series approach, we notice that the exponential of the identity matrix times t is equal to this matrix that has exponential of t on the diagonal. That's neat. If we test something else, something like the matrix 2 and that has 2 and 3 on the diagonal and 0 everywhere else, we notice the same thing. If we multiply this matrix by itself, the elements that are non-zero will still be on the diagonal. So we can still do this shift between exponential of the matrix that has 2 and 3 on the diagonal and 0 everywhere else times time is equal to the matrix that has exponentials on the diagonal and 0 everywhere else. But this is not true for any other matrix. We have, for example, already computed the solution of x prime equals 1, 2, 5, 4 multiplied by x, and that is not exponential of t, exponential of 2t, exponential of 5t, exponential of 4t. From the previous exercises, we know that it has a much more complicated form. Why? Well, in this section, we'll try to explain this. Let's think of a topic we have been covering a lot over the last couple of weeks, eigenpairs. Let's take psi and lambda being eigenpairs of A. Then A multiplied by psi equals lambda psi. So if psi1, psi2 to psi(n) is linearly independent, if psi1, psi2, and psi2 are linearly independent, if they are independent, then we can start writing them like this. We can start writing A times psi1 equals lambda 1 psi1. And then if we also want to talk about psi2, we then have n rows, 2 columns matrices, in which we're multiplying A times the column psi1 and the column psi2, and we retrieve lambda 1 psi1, lambda 2 psi2. And we can do this n times. Why does it still matter for them to be linearly independent? Not yet. But now we can write the matrix T as the sequence of linearly independent eigenvectors of A, so xi1, xi2, xi3, down to xn. And the right-hand side is that same matrix multiplied by the first column is multiplied by lambda 1, the second column by lambda 2, the last column by lambda n. That is equivalent to say that it's T multiplied on the right by the diagonal matrix that has the eigenvalues on the diagonal. We'll call that D. So it holds that A multiplied by T is equal to T multiplied by D. If our eigenvectors are linearly independent, then we can invert T. And we have A equals to T times D times T at the minus 1. If this holds, we call it the similarity transform. We say that A is diagonalizable and that A is similar to D. Why is it similar to D? Because we have a way to go from A to D and from D to A. This is why we need the invertibility of T, and this is why we need the linearly independent eigenvectors. If we don't have linearly independent eigenvectors, this is hopeless. We can still build T and D, but we cannot invert T. And that is a major element in this diagonalizable statement. On top of this, if A has a specific form, that is that A is equal to the transpose of the conjugate of A, we say that A is Hermitian in this case, and you choose the eigenvectors such that the product between one eigenvector and itself is equal to 1. We say that this is normalized eigenvectors. Then the inverse of T is trivial, is the adjoint of T, that is the transpose of the conjugate. So if A is equal to the transpose of the conjugate of A, and we choose normalized eigenvectors, then the inverse of T is the transpose of the conjugate of T. So let's do an example. Let's take a matrix 3, 4, 5, 2. And we want to find its similarity transform. The first step is we compute the eigenvalues. We find the eigenvalues being -2 and 7. Now that we have the eigenvalues, we want to find the eigenvectors. We find the eigenvectors -4, 5, and 1, 1. So immediately, as soon as we have the eigenvectors, we can construct T. And T is -4, 5, 1, 1. So in the first column, we have the first eigenvector, and in the second column is the second eigenvector. Remember that eigenvectors are defined up to a constant. That means we can multiply any column of T by any value, and it's still a legit way of writing T. What we have to do is then computing the inverse. So the inverse is not this. Why? Well, two key elements. First, A is not equal to the conjugate of the transpose. Then we haven't even normalized the eigenvectors. So two key reasons why just inverting T by taking the transpose doesn't work. We have to do the work. So in order to compute T at the -1, we have to write T and the identity and transform it until we have the identity on the left. So we have the T that is -4, 1, 5, 1, and we want to get to 1, 0, 0, 1. My first step was subtracting the second line from the first line, then rescaling the first line such that the first element is 1 and not -9, so dividing the first line by -9, and now subtracting 5 times the first line from the second line. So now we have the inverse of T, -1/9, 1/9, 5/9, 4/9. So we have D, that is the matrix with the eigenvalues on the diagonal. So D is -2, 0, 0, 7. And we have the formula that A is equal to T times D times T -1. And I'd like you to check this out. So we have written A as 3452, T is -4151, D is -2007, and T minus 1 is -1/9, 1/9, 5/9, 4/9. Check it out.